Okay, now we're gonna talk about priority scheduling, and this is how it looks in the C programming. Okay, this program, in general, this program effectively demonstrates how priority scheduling works, prioritizing processes based on the urgency or importance as defined by their priority values. Lower priority values represent higher importance in the context. And now we're going to explain to how it works in the program, how it looks like in the code. Okay, explanation sorting by priority. The nested loop structure sorts by the processes based on their priorities. The inner loop identifies processes with the smallest number and swaps it with the current process in the outer loop. Calculating metrics as each process completes the code updates cumulative turnaround time and calculates waiting time. For each process, turnaround time is the total time for the start until a process completes here. And waiting time is calculated as turnaround time minus the burst time. Okay, do you understand it? So we can understand that 8 minus 8 is equal to 0. And this is 23 minus 5 is equal to 18. Okay, I hope you understand it. And this is how it uh, looks our output. We can see the average waiting time. This is the average waiting time of these three. And turnaround time, this. So I hope you understand it. Okay, now we are going to talk about shortest job first. Shortest job first is actually a non-primitive scheduling algorithm where the process with the smallest execution time is selected to execute next. So it takes first the shortest, like the shortest, smallest execution time that process needs, and it executes it first. Okay, shortest job first can significantly reduce the average waiting time for processes in the system, which is beneficial in scenarios where job lengths vary significantly. So this is how it looks in our C programming language. Uh, this loop is for sorting our processes by the burst time. And this is our, yes, and this is calculations here. Okay, the algorithm starts by sorting the array of processes based on their burst times using a selection sort method. This step is crucial as it aligns the processes in the order they should be executed. Okay, the waiting time for the first process is 0. For each subsequent process, the waiting time is the sum of burst times of all the previous processes. The waiting time for the first process, or the turnaround time for a process is the sum of its waiting time and its burst time. So this represents the total time from the when the process was submitted until it is completed. So this is how it looks, our output. Turnaround time is this one, waiting time is this one, burst time is this, and process IDs is like looks like this. Why it looks like this? Because it has sorted here. So the ID, so the process ID with the 4 ID is the smallest. It has the smallest burst time, and the process ID 2, it has the biggest burst time here. So, and this is sum. Waiting, the turnaround time is the sum of burst time and waiting time here. As you can see, 3 plus 0 is 3, 6 plus 3 is 9, 7 plus 9 is 16, 8 plus 16 is 24. An average waiting time is just the sum of all these waiting time values and dividing by how many process IDs are there for. And turnaround time works the same. It it the sum of values turnaround time and dividing by 4 because there's 4 processes. I hope you understand it. Thank you. Goodbye. Hello everyone. Today we're going to talk about round robin scheduling. Okay, now we see here. This code effectively demonstrates how the round-robin scheduling algorithm operates by ensuring each process receives a fair amount of CPU time, managing time with a circular queue mechanism, and providing insights into process management without turnaround and waiting time calculation. This setup is ideal for understanding basic process scheduling in operating system. Okay, this is the our output here, and I will tell now how it works. Okay, according to details, uh, the burst times of the processes are copied into the temp, yes, array for modification during scheduling without altering the original burst times. Okay, and here, the loop continues until all processes, until x doesn't equal to 0, have completed. Now, inside the loop, each process gets a chance to execute for the duration of the quantum for its remaining burst time, whichever is less. Total, total, yes, here is it. Okay, total is updated by either the quantum or the remaining burst time of the current process. And check if a process complete, or we can say temp when temp's element is equals to 0. Update the waiting and the turnaround times and print the process details. Okay, and processes, this is the quantum check. Processes that do not complete within one quantum are reduced by the quantum amount, and total is updated accordingly. Round robin behavior. After addressing a process, the index I, yes, is adjusted to loop back to the start after reaching the end, mimicking a circular queue. Okay, and this is our output. Here we get average waiting time, and average turnaround time. This is the our processes.